When we think of modern railway safety, our minds usually jump straight to the high-tech stuff, right? We picture advanced sensors, automated braking systems, and massive control centers just wall-to-wall with blinking lights. But underneath all of that incredible technology is a fascinating reality. Railway safety isn't just about flawless machines. It's fundamentally about the vital, and sometimes pretty fragile interaction between human operators and the intensely complex tech they manage every single day. Welcome to This Explainer. Today, we're going to dive deep into operability, human factors, and exactly why the human element remains the absolute most critical component of railway safety.
So let's kick things off with a crucial question. What actually happens when the fail-safe fails? It's really tempting to just assume automated logic can step in and prevent all disasters, but let's try a quick thought experiment. Think about the last time you were driving, and suddenly a dashboard warning light flashed red. Or maybe your GPS just completely lost its signal right in the middle of a chaotic, busy intersection. You definitely felt a spike in adrenaline, didn't you? Now scale that feeling up to a multi-ton train carrying hundreds of passengers at high speeds. We really have to frame human error as a universal, unavoidable experience. We are dealing with massive mechanical and electrical systems, and inevitably they wear down, short out, or just plain break, and when they do, a human has to step in. Relying on human judgment when things go wrong, especially under intense, compounding stress, completely changes the entire safety equation.
To understand how the industry handles this, we'll walk through a highly structured framework. We're going to cover the human element, reliability and manual workarounds, how to design against error, what makes a competent maintainer, and finally, how products, processes, and people all tie together.
All right, Section 1, the human element, and designing for the human operator.
Let's lock down a definition for operability. Basically, it's the ability of a system to be operated safely and effectively by its human staff. This means any system design absolutely has to account for the actual people running it. We see this all the time where products are engineered to be perfectly safe under theoretical lab condition fault scenarios. Engineers, they love to focus purely on the math, the physics, the logic of a system. But we can't forget the messy reality that living, breathing people have to use these tools. If you've got a brilliant piece of software, but it requires an operator to flip through a massive, bulky manual in the pouring rain just to figure out what a critical alarm means, well, that system has terrible operability. You can't just expect operators to execute instructions perfectly every single time without fail. The system has to be designed to work in harmony with our natural cognitive and physical limits, especially when we're exhausted or totally overwhelmed.
Picture this for a second. You're out there navigating an incredibly complex, dangerous web of railway tracks, dodging high voltages and fast-moving trains. And you're doing this in the dead of night, or maybe right in the middle of a blinding rainstorm. This right here is where theoretical safety concepts crash headfirst into high-stakes, real-world conditions. A perfectly designed digital interface sitting in some warm, cozy engineering office means absolutely nothing if the physical environment it creates on the ground exposes technicians to unacceptable harm. True operability demands that we start by looking at the human, standing out on the ballast, dealing with heavy machinery, and we design outward from their physical reality.
Moving on to Section 2. Let's talk about reliability, manual workarounds, and the real danger of system failure. You might be wondering, why does a signaling system with poor reliability actually make the railway less safe? It's not just about trains running 15 minutes late, it goes way deeper. Think about the conceptual difference between a fail-safe automated system and a manual workaround. An automated system is built to seamlessly protect the operation. If a component snaps, the system is programmed to instantly default to a safe state, like automatically turning all track signals to red to stop every train in its tracks. But if that automated system goes offline and the railway still has to move passengers, operators are forced to rely on manual workarounds. And by their very nature, these manual procedures completely strip away those built-in automated protections.
So it boils down to this. Poor system reliability directly forces the signal operator to use manual procedures way more frequently, just to keep the trains running. And because manual procedures rely entirely on human judgment, they are inherently so much less safe. Just imagine the cognitive load on an operator during a massive system outage. Alarms are blaring, dispatchers are screaming on the radio, and the pressure to avoid a massive delay is just immense. As humans, we are notoriously unreliable when trying to carry out complex instructions under highly stressful, degraded conditions. The less reliable the machine is, the more pressure we drop squarely onto the human operator's shoulders, and that exponentially increases the risk of a fatal error.
That brings us to Section 3, designing against error by engineering physical barriers.
If we know humans are going to make mistakes under pressure, how do we actually fight back against that natural fallibility? Well, if we look back at historic lever frames from early railroading, we can see the brilliant evolution of mechanical safety interfaces. The goal for engineers has always been to build systems that physically block operators from creating an unsafe situation. In those old mechanical interlocking systems, if an operator tried to pull a lever to clear a signal for a train, but the track wasn't safely locked and confirmed empty, the lever physically would not move. The heavy iron mechanism defaulted to a safe state and literally refused to let the human make a mistake. And today, we apply that exact same philosophy to modern digital and electrical systems.
To hit that level of safety today, engineers rely on a hierarchy of error prevention. At the bottom, you have your basic administrative controls. We're talking easy-to-follow maintenance instructions or moving away from giant paper binders to encapsulated checklists on mobile devices. And sure, clear instructions are great, but relying on them is actually the lowest level of risk reduction. Why? Because human attention naturally drifts. Fatigue sets in. Workers rush to finish a job because it's freezing outside. Administrative controls essentially ask the human to consciously choose to be safe. Engineers know they have to aim significantly higher up the hierarchy to truly stop errors before they even happen.
To get to that absolute highest level of error prevention, engineers use what's called error-resistant design. A really classic, highly effective example of this is pin coding plug-in modules. Instead of just slapping a warning label or a piece of colored tape on a wire and crossing their fingers that the technician pays attention, engineers design the physical plug so it can literally only fit into the one correct socket. By putting a simple physical barrier in place, performing the wrong action becomes physically impossible. It completely removes the burden of human choice and judgment from the equation, which makes the whole system vastly more resilient to things like fatigue or distraction. Section 4. The competent maintainer, and going way beyond basic training.
Look, you can build the safest, most brilliantly error-resistant machine in the world, but if the person fixing it doesn't know what they're doing, the entire system is instantly compromised. Safe maintenance demands frontline staff who are not just trained, but demonstrably competent for specific safety-critical tasks. And competency isn't just about sitting in a quiet classroom and passing a multiple-choice test. It encompasses the actual behaviors someone exhibits on the job, especially when under stress. Put yourself in this scenario. A critical signal fails at 2 a.m. in freezing rain. High-speed passenger trains are backing up. Dispatchers are demanding a fix right now. Can that maintainer safely troubleshoot the issue without panicking or taking a dangerous shortcut? That ability to hold the line on safety when the pressure is immense, that is true competence.
Building that kind of deep, reliable competence is definitely not an accident. It is a rigorous, continuous journey. It starts right at the beginning, with careful selection and confirming the medical suitability of an applicant for what is a highly demanding physical role. After that comes intensive, accredited training to build the foundation. But theory isn't enough. The worker then goes through strict workplace assessment and supervised experience on the actual equipment. Finally, and this applies even to a seasoned veteran with 30 years on the job, every single shift involves a rigorous on-site safety briefing before their boots ever touch the ballast. They identify the specific layout, the live tracks, the exact safe working arrangements for that specific day. Competence is a continuous, tightly managed cycle of intense preparation and hyper-specific situational awareness.
And finally, Section 5. Products, processes, and people. The unified cycle of safety.
At the end of the day, a reliable and safe railway system relies on a continuous monitoring loop. Think of it as having 3 essential interconnected slices. First, the products. This is the technical hardware, the signals, track circuits, the interlockings. Second, the processes. This is the operating framework, the strict rulebooks, the maintenance schedules, the safety protocols. And third, the people, the staff competence, the drivers, and the maintainers we were just talking about. Railway safety is an emergent property. It absolutely does not exist in the hardware alone or just in the rules. It only exists when all 3 of these domains, products, processes, and people, function together perfectly.
And this brings up a crucial point. Change any one of these elements and the entire balance of operations shifts. Mitigating one risk almost always introduces a new one. If you roll out a brand new, highly advanced piece of hardware, you've changed the product. But if you don't simultaneously update the process of how to inspect it, or thoroughly train the people operating it, the balance is broken. A failure or a misaligned change in just one of these 3 pillars puts immense, sometimes fatal pressure on the entire system. You literally cannot upgrade the machine without also upgrading the human and the rules they follow. We're moving really fast toward increasingly automated railways, with sophisticated algorithms taking over more of the driving, routing, and signaling. But when that technology inevitably degrades,
It's still the human who has to step out into the dark and fix it. As these systems become fully autonomous, operators are going to get less daily, hands-on practice managing the complex mechanics of the railway. And that creates a really profound tension. Moving forward, will the human element become our greatest liability, prone to rust and confusion, or will they remain our ultimate, irreplaceable failsafe? It is a question every design engineer, every operator, and honestly, every one of us who rides the rails is going to have to continuously wrestle with. Thanks for joining me on this explainer.